We have seen that the current position of a point is represented by the motion, which is a function of the initial position of the point and the time. We have also seen that a small line segment emanating from capital X maps to a small line segment emanating from small x according to this relation. So we have defined the motion, we have defined the deformation gradient, and then we have seen how we measure the relative change in length of these line segments. We measure that through uh, large strain displacement relationships of this sort, which defines the Green-Lagrange tensor. You have a similar expression for the Almanji tensor and other strain tensors that you can think of. Now, we are going to look at how volumes map. So, how do we connect volumes in the reference configuration to volumes in the deformed configuration? To do that, we first have to recall a couple of results. So, if a volume is defined by three vectors, let's call them u, v, and w. So the volume that we are talking about is a parallelogram that's formed by these three vectors u, v, and w. Then this volume can be represented by the triple product of these three vectors. Triple product has some rules which you might have learned on your course in vector algebra, and these triple products, we will represent them by the square brackets. So u, v, and w would mean triple product of u, v, and w. So which is given by this, but there are other, this can be cyclic combinations of this also are equal to u, v, and w. But that's a different point. Result, another result that we need to look at is if we know the triple product of say u, v, w, the triple product of tu, tv, tw, where t is an arbitrary second order tensor, is given by I3 times the triple product of u, v, w, where I3 is the determinant of t. So if you multiply all these vectors by a second order tensor to get another vector, the volume enclosed by those three vectors is determinant of t times the volume enclosed by u, v, and w. That's the result. This result can be proved. I have a proof in the next slide, but I'm not going to explain it. It's self-explanatory. Please go through it. So using this, we can actually find out how volumes map from the current to from the reference to the current configuration. So let's say this is a volume D capital V in the reference configuration at a point capital X, and this volume is given by okay, this volume maps to the volume d small v in the deformed configuration at the point small x. Capital X and small x are maps of each other. So to calculate this volume, what I will do is I'll take vectors along this edge, and this edge, and this vectors are dx1, dx2, and dx3, and the small volume is the triple product of these three vectors. Now this volume had been mapped from volume in the reference configuration, so that dx1 is mapped from d capital X1. So dx1 would be f times d capital X1. Similarly, dx2 is mapped from d capital X2, and this, so d small x1 would be f times d capital X2 and f times d capital X3. Using the theorem that we have learned in the previous slide, we know that this is equal to det f and the triple product of dx1, dx2, dx3. This det f is given a special name. We call it the j. Remember earlier we had talked about a j zeta, where this was the Jacobian for the mapping, the isoparametric mapping. So this is connected to the finite element part. But this j is also the Jacobian of this transformation. So Jacobian of this mapping is this j, and this j actually connects the volume. This volume is d capital V, of course. So connects the volume d capital V to this volume d small v. So every volume d capital V is mapped to d small v through this scalar quantity j, which is the determinant of the deformation gradient. Now obviously j cannot be 0. If j becomes 0, then this volume will shrink to a point. Remember, we are talking about one-to-one motions where every point maps onto one and only one point. If this whole volume collapses to a point, then um, then we don't have one-to-oneness anymore. So j equal to 0 is not allowed. J equal to negative is also not allowed, because that means that this triple product, this triple product and this triple product don't have the same sign. So the volume actually flips, which means that one of these axes flips and you get a different sign of the triple product. That is also not allowable. So therefore, we have to have this condition that j is greater than equal to 0. J is greater than 0, strictly greater than 0 all the time, for the kind of well-behaved motions that we are looking at for the time being. Okay, now this is how volumes map. So three kinds of maps. Points map through the motion, line segments map through the deformation gradient, volumes map through the Jacobian of the deformation gradient. Now let us look at this situation where we have an area. So with every area we can correspond a vector. So this small area ds on the surface of the body can be represented by a vector ds, which is n, the normal to the area, times the scalar area. Similarly, d small s is a vector which is uh, normal to this deformed vector, times d small s. So this red patch maps to this red patch due to the deformation, and we are trying to figure out what is the relation between this patch and this patch. What is the area, the normal of this patch versus this patch. So to do that, we will use the result of the previous slide, and we'll make a volume out of it. So for the volume, this will, let's say this is d capital X, some vector. It maps to this volume where this is d small x, and we already know that the volume of this would be ds dotted with d capital X. That would be the volume of this, and the volume of this would be d small s dotted with d small s dotted with d small x. Now these two volumes we know are connected through j. So this is equal to j times d capital S dot d capital X. Okay. Therefore, we have this d small s dot d capital X is equal to j times d capital S dot d capital X. Then here we have ds dot, this is f times d capital X, which is equal to j d capital S dot d small x. Now we have the relation here. Uh, ds can be represented by small n times the scalar area. The capital S can be represented by these are vectors. This is a vector. So this vector can be represented by capital N times d capital S. And now we have dx on both sides. So we can now find the relation between n ds, which is d vector s. So this is n ds. This is capital N d capital S, the scalar, and they are related by jf minus transpose, which is easy to derive from here. So we are finding a relation between n ds and capital N d capital S, and that turns out to be j times f minus transpose capital N. So it's also written as n ds equal to j f minus transpose capital N d capital S. So this is this area, and this is this area, and the mapping between them is j minus f transpose. This is a very important relation that we will need when we deal with stresses and so on. So this is called a Nansen's relation. So we have one more mapping. We know that areas in the deformed configuration are connected to areas in the reference configuration through JF minus transpose.